Thank you. So as you will notice during my 3 lectures and Florent's lectures, the 2 series are very closely related. Yet the way I will start today, I will start about a completely different problem. It's my favorite problem, and somehow I will use it. Well, first I will motivate it because it's interested on its own, and then I will use it as an example on which I will build a methodology. Because you heard Florent's lecture and you heard some interesting connections, basically writing Bayesian posterior probability distributions as Boltzmann distributions with some Hamiltonians that maybe are related to some nulls that we know how to study in physics. But so far, it was just kind of a dictionary. So far, Florent just reformulated results well known in statistics, in statistical physics language. So that's not why we are doing it. Like, we are studying this field because the methods we develop in statistical physics actually get something new that people didn't know in statistics or information theory, and that's what we want to tell you about somehow at the end of these 2 series. But for that, I need to build what is our asset, and that's the methodology. So I will do that on a problem that is, so I just keep this triangle. So the problem I will be telling you about today is coloring of graphs. And this, here we had information theory, statistical inference, and coloring of graphs would probably belong to computer science or computer science or combinatorics, graph theory, discrete math. I don't know, discrete math. Well, all these people would be really interested in various aspects of graph coloring. So that would be like 1, 2, 3, and I will be telling you about how physics is actually useful to solve these problems. So to solve problems in these disciplines on this example of graph coloring. Okay. So let me first, let me start slowly and first of all define what's a graph. So graph is defined on a set of nodes and set of edges. So an example of a graph would be, I don't know, like this. So I would have 1, 2, 3, 6. So I would be, I will be indices for the nodes, and here I have graph of 6 nodes. So the size of the set of nodes here is 6. In general, it will be capital N. And then some of these nodes are connected with edges. So let's see, I don't know, like this, for instance. And so I will have ij belongs to the edges if and only if the node I and j are connected. And I will also define the number of edges, so the size of this set, and that will be capital M. Okay, then, for instance, I can define something like the average degree of the graph, which will be twice the number of edges divided by the number of nodes. Right, so this I will be using like average degree. Actually, before defining average degree, I should define a degree. So let me define a degree of node I. And degree of node I will say is di, and it will just be the size of the size of set of nodes such that I and j are neighbors. Okay, so the number of nodes to which a node is connected is the degree. So this guy, for instance, index, 1, will be connected to 3 other nodes, so its degree is 3. And then this number is the average degree. It's the sum over everybody divided by n. Okay, so that would be about graphs. Now graph coloring. So I was fortunate enough that there are nice colors here. So how do I define graph coloring problem? So let's see, 4 colors. Well, that should be more than enough. But let me, oh no, I have a triangle here. Okay, so good. So now graph coloring. Is the following problem. So we assign some numbers Si to every node I, and so mathematically this Si will be in the set from 1, 2 up to some q, So here I have Q equal to 4, so I have 4 colors. So this will be indices for colors, okay? And now the goal is to assign each node a color such that if ij is an edge, then Si is not Sj. That's the rule of the game. Okay, so let's see for this little graph, how do we do that? So do you think I can do that? So of course, the more colors I have, the easier it is. Like if Q is equal to N, then like any coloring works. That is not repeating colors, but the goal will be to color a given graph with as small number of colors as possible. So let's see if I can do 2 here. Can I color this graph with 2 colors? Or do I need more? That's an easy question. It's enough to notice that there is a triangle in this graph. And triangle cannot be colored with 2 colors, right? How would I do that? Because if I do this one green and this one blue, this cannot be green and this cannot be blue, because otherwise I would violate this constraint. So I will call this guy here constraint. Graph coloring is an example of constraint satisfaction problem. I have constraints and I want to satisfy them all. Constraint satisfaction problem. So let's get back to this graph. So I cannot, because if this one was blue, then this edge does not have that constraint satisfied, right? Edge cannot be monochromatic, cannot have the same color on both sides. So if I have a triangle, it's clear that I cannot do with 2. I have to have at least 3. And then that should be enough, because then, I can do this one orange, for instance, and this one blue, and this one blue. And I could have many other possibilities how to color it to satisfy all the constraints. Okay, so that's graph coloring. So this problem is, known in mathematics for a long time. Just checking. Okay, or maybe oh, that's all right. So what can we, that's it. I forgot to say a few things about graphs, but I will say it later. Okay. So somehow the most famous example of why graph coloring is widely known in mathematics and studied is this thing that coloring of maps. So when you look in an atlas and the countries are colored in different colors, and of course you want to color countries that are neighbors with a different color, so that you can distinguish them on the map. So this map coloring is actually equivalent to graph coloring. So this is a little country in the middle of Europe where I come from, and these are the regions, so I colored them. Neighbors have different colors. And how do you go from a map like that to a graph? So to the setting that I was defining, right? You just, instead of these countries, you have the nodes of the graph, and they are colored. And you have the edges. Edge is between 2 nodes whenever they are actually neighbors. They have some part of the border that goes between the 2 of them, and then you forget about the map, and you end up with a graph. Okay? So coloring of maps is particular, because when you transform it to a graph, it leads to something that is called a planar graph. That means that you can draw this graph into a plane in such that there exists at least one drawing of that graph in a plane, so that no 2 edges are crossing. See, for instance, here in my figure, I have edges crossing, but this is because just I draw it in a sloppy way. I could also put this node somehow up here, and I could very well draw this graph without edge crossing. But say graph like that, with 4 nodes and fully connected. Oh, this one is still fine, but let's say 5 nodes. Okay, so this one, you can think about it. This one cannot be. I hope so. No, this one still can. Okay, if you have dense enough click, by far not all graphs can be drawn in such a way. So coloring of maps. It's a very famous problem, because basically 200 years ago, or I noted somewhere here the exact year, in 1852, somebody called Guthrie, who was studying, who was a cartograph, and he was studying this graph coloring. He observed empirically that whatever map he had, he could always color it with 4 colors. And mathematically, it was a very interesting question, is it always true? Or is there a map, maybe a very particular one, that cannot be colored with 4 colors, for which you need more than 4 colors? So, for 200 years, nobody was able to find a counterexample, but also nobody was able to find a proof. And it was one of the most famous problems, basically, in math, in graph theory. And that's why somehow, every lover of mathematics knows about the 4-color conjecture. By the year of 1976, in which it was proven by Appel and Hakim. No. Sorry? The statement of the conjecture is that whenever you have a planar graph, so graph that can be drawn in a plane without edge crossing, then there exists a coloring with only 4 colors. It's very, okay, it takes maybe 10 minutes. It's a good exercise in discrete math lectures to show that you can do it with 5 colors for planar graphs. But for 4 colors, it's much more challenging. And actually, there's a really interesting story about that the first proofs that came, they were heavily using computer-aided proofs. So many people in math actually didn't like it. They basically constructed a set of examples, and if a computer finds colorings for those examples, then the theorem holds. But and then they had a supercomputer running for several months testing all those examples. So that's not a kind of proof that people have in math, right? And okay, since then, now they are also elegant proofs of that. But that's somehow where many people became aware of graph coloring. So. But we will not be, in this lecture, we will not be so much concerned about the planar graphs and about the maps. But the kind of graphs that we will be looking at look more like something like this. And that's actually random graphs. So we will be concerned with coloring random graphs. So what's a random graph? So graph coloring, and here I can go with random graphs. Random graph. So, we will still be denoting it. Okay, let me see. So I will be denoting random graph, G, N, and P. So N still stands for N nodes. N here stands for N nodes. Okay, and P is a probability. So I will have that. The way to construct this graph is that for every possible ij, we put, okay, I didn't define something that I will need now. So adjacency matrix here, where do I have the edges here? If ij is in an edge, then I say that aij, which is called the adjacency matrix of that graph, is 1. And if ij is not an edge, then aij is 0. Okay, and I don't know, AII, for instance, we will say it's 0, that nodes are not connected to each other, there are no self-loops. So this will be adjacency matrix. So that's a notation that will somehow become useful. Maybe, with the notation here, maybe here I define this set J, which were all the neighbors of E. So, just to make it shorter, I will call this set the neighborhood of I. And the size of the neighborhood of I will be the degree, okay? So this kind of a Carl sign that, from the partial derivative of I, that will be the nodes that are immediate neighbors of the node I. Okay, that will come up with a lot of the equations that you will see in the next 3 lectures. Okay, so back to random graphs. So for every j, we say that aij is 1 with probability p and is 0 otherwise. Okay, so that's how, so we go like, what about this pair? We throw a coin, no edge. Because coin, not a coin, we flip a random number generator in the computer, it's bigger than p, so no edge. For this pair, it's smaller than p, so we put an edge. For this pair, it's smaller than p, we put an edge, here we etc., and this way we throw in some edges. and that will create a random graph. And so now the question is such a random graph colorable with a given number of colors? So of course the fact if it is colorable or not is this number Q. And random graph coloring, okay, why not? It's an interesting problem as any other version of the coloring problem that we could think about. But okay, that's the problem that we will be talking about, and now I want to motivate somehow why is that interesting. So first of all, I should probably finish with some observations for the random graphs. So first of all, we will be, the Q, the number of colors we have. The reason could be that here I have a finite number of colors at the blackboard, so we will be looking at the case where the number of colors is some fixed number, say 3 or 10, but it's some fixed number. It's not growing when n is growing, whereas the size of the graph will be growing, right? That will be our thermodynamic limit. We will go to some case where basically we will build a statistical physics model on that graph, so this will be our thermodynamic limit. So how should this P scale such that the graph coloring is interesting? Okay, so if the graph is if the P is really small, then basically how does a random graph look like? We just have few edges there, and it may not even have a giant component. So if it doesn't even have a giant component, then for instance, then it's basically a set of trees, so it may be colorable with 2 colors, maybe 3, but with very few colors. So what's somehow the interesting setting? So it will turn out that the interesting setting is that when P is some constant, divided by n. So what does it mean? What is this constant? So I will call this constant C, and it's not by chance that is the same C as here, because if you think about it, when n is large, and you have n minus 1 possible neighbors, on average, so if n is large, minus 1 you neglect it, on average you will have C neighbors. So if C is a constant, you have on average C neighbors, and what's the probability distribution of how many neighbors you have. So this you can work it out as an exercise. So the degree distribution, the probability that your degree is k, is just a Poisson. So okay, C factor. No, C to the k, right? Up C to the k. So this and k factor. Okay. So C can be any real number, k is the degree, so that's an integer number, and probability that a node has degree k is this Poisson degree distribution. Okay, that's a very basic property about sparse random graphs. So once I wrote that, this means that our random graphs are sparse. Okay, and now how do we persuade each other that this is the interesting setting where graph coloring is interesting? So let's try to do some first kind of calculations about graph coloring. So let's fix the number Q. And the first thing we could try to estimate is, given n goes to infinity and we have some random graph with average degree C, what is the number of colorings it typically has? Okay, so this, we will call it, so the number of colorings of a given graph will be Z of G, because it will end up to be the partition function of our statistical physics model. So this is, this is the number of sets Si when I goes to n, from 1 to n, such that this set is a valid coloring, so colorings. Just writing it schematically. So what is the number of these colorings for a given graph? So this is not easy to evaluate, right? Because we have, if we have n nodes, we have q to the n possibilities how to put the colors in. So we could exhaustively go over through of them. That would take a lot of time. So let's, we could compute some averages. So one average that is easy to compute is actually, let's just compute the average over all possible graphs of a given number of nodes. And for simplicity, I changed slightly here from fixing the probability of putting an edge, I put a given number of edges. Okay, this is like going from the canonical to the microcanonical ensemble. For all purposes of this lecture, these two ensembles will be equivalent. Of course, they are not strictly equivalent, like some large deviation properties are different, but all these properties will be irrelevant for our lecture. So sometimes I will be working with fixed probability and sometimes with fixed number of edges. And this C and number of edges are still related in this way. So what's the average of the Z of G? So how do we compute that thing? So this is something that is easy to compute. When you think about it, what is it basically? It's I could also. There are several ways to write it, but I don't know if many of them are. Okay, let me maybe start directly with this. So when you think what's the average of the number of colorings over all possible graphs, it's since Z is a sum over all possible colorings of some indicator function that's indeed a coloring, and average is also a sum, you can switch the two sums. And instead of fixing the graph, you fix first the coloring, and hence you multiply by all possible numbers of colorings, but not necessarily valid ones. And then here what you need to write is a probability that a random, so I should not be saying coloring, that a random assignment of colors to nodes of whatever colors to nodes is a valid coloring. Well, okay, it's a bit it's longer to write than right. You agree with that's the right thing. So it's the number of possible assignments of colors to nodes times the probability that random such assignment is a valid coloring. That gives you the expectation of the number of colorings that the graph has. And now this thing is easy to compute because we are putting the edges in independently, right? And we have m edges. And for each of these edges, the probability that we put it between two nodes that have different color is simply 1 minus 1 over q. Right? Because if I randomly throw in colors on q colors on the nodes, then the probability that if I choose randomly a pair, they have two colors, is just 1 over q. And I want the probability that they do not have the same colors, so that's 1 minus 1 over q. And I have m edges, and I'm throwing them independently. That's by the definition of the random graph. So this means this probability just gets power m. Okay? So good. So it's quite a simple expression, right? So what can we learn from it? So let's define something familiar in physics. I will call it the annual entropy. So the annual entropy, I've anticipated this will be kind of a partition function. So the annual entropy is the expectation of the partition function is the logarithm, and I forgot the logarithm. So again, is the logarithm of the expectation of the partition function over the g, right? So from what we computed there and divided, because entropy, as usual in physics, is an extensive quantity, so we divide by, so the volume here will be the number of nodes. So I divide by the number of nodes, and then what this will be, so just from our expression, so I have n, I divide by n log q, and here I have plus m over n log 1 minus 1 over q. Okay, and m over n is just c half. So let me replace m over n, number of edges by number of nodes, that's the average degree half. Sorry, z? Zg? Zg is the number of assignments of colors of nodes that are valid colorings. Yes. So it's something between 0 and q to the n. You can just go through all of them, and if it is okay, you say you count 1 plus. Okay, so then average over all graphs of that is just this number. And okay, and it gives you some entropy of this kind. But now when you draw this entropy, so let me draw this as an yield as a function of this average degree c. And you see that q, q is something bigger than 2 at least, right? So logarithm 1 minus 1 over q is a negative number. So this is something decreasing and going to 0 at something that I will call C annulled. So the annulled threshold, that is just, when is this expression equal to 0? This is when C is equal to twice logarithm of q divided by logarithm of 1 minus 1 over q with the minus. Okay, so what does this mean? So this is already, and for a q that is a constant, C will be some constant. So I wrote some numbers here about what it is for, where do I have them? Here. So for instance, when q is 3, the C annulled is something like 5.42. When q is 4, so with 4 colors, the C annulled is something like 9.64. Okay, and when it's 5, it's something like 14.4. And we will also be interested in the limit when q is large. And you see that when q is large, then this is small thing. You can develop the logarithm here. And you get that when q is large, this C annulled goes like 2 q log q. Right, the q comes from here. That's the first order expansion of this little expression. Okay, so you see that these are some constants. So that's somehow justifying that this is the right kind of scaling here, because when the graph is really sparse, means the C, for instance, is smaller than 1, it means that the graph doesn't even percolate, then we can color it with very few colors. So there will be, we will be able to find some really trivial lower bound on how many colors we need. Maybe the percolation is even too much. Even before we have Q core, a graph can be colored with Q colors. So there's some trivial lower bound. And now we have this C annulled. So what's the status of that actually? Let's think about it. So first of all, if this annulled entropy is negative, then what does it mean here? We are averaging some numbers that is either 0 or 1 or 2 up to q to the n. And if this number S annulled is negative, it means that this average is exponentially small, right? But since this number was an integer, 0, 1, etc., then it means that with high probability this number must have been 0. Because how else can we average integer numbers and get something exponentially small in n? So this is telling us, completely rigorously, that whenever this S annulled is negative, then with high probability a random graph will not have a random coloring, will not have a coloring with this number of colors. So this is kind of an upper bound on where the interesting things are happening. Okay, what about the other way around? So what if S annulled is positive, so in this region? Does that mean that with high probability a random graph has a valid coloring with that number of colors or not? So who thinks that yes? Who thinks that yes? Who thinks that it doesn't mean that? So let's think about it, because that's kind of, Florent was talking about this limit of high dimensional statistics. This is kind of the kind of math that gets maybe not intuitive at first when we are having this kind of high dimensional limit, when the number of constraints is M here, is proportional to the number of variables we have to estimate. It's not much bigger, it's not much smaller, it's right somehow in the regime where interesting things are happening. And when this number of proper colorings is, well, either it's typically 0 or it is typically not 0, but in that case it will be exponentially large, right? This will be some system, the entropy is typically extensive. It's not something like, it's n times some constant. It's not something like, I don't know, 1 over log n, or entropy is extensive. So typically, if we have proper colorings, we will have exponentially many of them. This you can also see even from the simple fact that, from this degree distribution, you know that there is a finite fraction of nodes that are not connected to anybody. And those can clearly take any color they want because they are not connected to anybody. So only that is giving you extensive, but it might be misleading, because even if your graph is, say, regular, say everybody has the same degree, you still have extensive entropy because of, for instance, if you have a valid coloring, that you must have some places where you can switch to colors or something like that. So how does the math of things that are exponentially large in n, when n goes to infinity, work? Right, then we are basically kicking something, we should be thinking about large deviations. And the thing is that quite generically, okay, let me define some, it's maybe a good point. I should maybe speed up a little bit. Well, but this is important, so let me define where S annealed is here. Let me define S quenched. So the quenched entropy. So this will be something more physical, to be related, but I switch the expectation and the logarithm. So I will still have the expectation over graphs, but now I put the logarithm inside. Now, okay, ZG might be 0, so just to be sure that this is never 0, because then logarithm is not defined. Let me put +1 here, but then since these things are typically exponentially large, it will not matter actually, because okay, I'm always thinking of the limit n to infinity here. Okay, so let's just think if switching this expectation with the logarithm can lead to something, very different or not. So in general, it does. In general, all we can say is that this quenched entropy is smaller or equal to the annealed one. So if I go to my picture, all we can say is that the quenched one must be somewhere below. It might be equal, but we don't know. A priori, it doesn't have to be equal. What can happen so that it's not equal? What can happen is that this annealed entropy can be positive if it can still be that typical graph has no coloring, but we have some rare graphs that have very, very many colorings. And if, say, with if the number of, if with probability 1 over n to some big power, say 100, a graph has, say, e to some exponential number of colorings, this will still lead to annealed entropy that is positive, right? But it will not lead to positive quenched entropy, because the fact that we take the logarithm here basically washes away these if the logarithm of z is fluctuating a little bit, that's fine. But if we exponentiate it and make the average on the z, then this is leading to wrong results. So all this to say is that in these type of problems, things that if we do usual calculations like taking first the expectation and then the log, or the other way around, it usually doesn't matter. In these type of problems, it crucially matters. And basically, the whole big part of the lecture will be about telling you, or trying to find together when these things are equal and when this quenched entropy is strictly smaller than the annealed entropy. And we know that it cannot be equal all the way. Why, for instance? Well, that's something that when people started to study these graphs, the first somehow remarkable conjecture they had, that is still a conjecture, not a theorem, is that indeed there is some kind of a threshold. So let's define C colorability, such that, so this will of course depend on the number of colors, and it will depend on this, well, that's all. It will depend on the number of colors. And the definition of that is, I should not be writing it here because it goes for the random graphs, but okay, you write it somewhere with the random graphs. So let me define C colorability here. So it's defined in this way. If the average degree is smaller than this C colorability, then a graph is, and I said that it depends on the number, is Q colorable with high probability. And if C is bigger than C colorable, then graph is not Q colorable with high probability. So there is this kind of a sharp phenomenon. As n goes to infinity, there is a well-defined number C col with this property. So from a physics point of view, this sounds reasonable. There is a phase transition. If everything is large before some threshold, critical threshold, coloring with high probability exists. After it doesn't, then we could take a computer, right, take graphs that are not too big, say 200 nodes, and run some exhaustive search and count these colorings and plot these things. That's what people actually have done. So let's see. Yes?
I got a little lost in the derivation part. Could you just like give a bird's perspective summary of the derivation, like the rationale?
The derivation of what? Of this annual entropy?
Yeah. Of the number of colors. Just kind of review.
Yeah. So what I was saying here that we can quite easily compute the average overall graphs of the number of colorings. This leads to this expression that I define as the annual entropy. And from annual entropy, when it crosses zero, we can define this annual, critical average degree. And now that I define this, let me now use this C colorable. Now that I define the true threshold, what basically we argued is that this C annual must be bigger or equal to the C colorable, because if this annual entropy is negative, then with high probability, this Z must really have been zero. And then I spent 5 minutes arguing that the converse is not true. That when this S annual is positive, it does not mean, that C annual is equal to C colorable. And now I am arguing based, on, we could try numerically estimate this C colorable, and we will see that it is smaller than this C annual, numerically. That there is, from numerical evidence, we can see that indeed this quenched entropy that I defined here, that is the same thing except I switched the logarithm and the average. This is kind of more informative, right? Because since this Z is exponentially large, logarithm somehow washes away the big fluctuations that are there, so averaging the logarithms tells something about the typical properties. And that's what we are interested in, because that's how we want to define all the things, right? I give you a typical graph, one of them, and you would like to talk about properties that will be true for a given sample, not on average over samples, because there are some rare samples that are crazy. So that's this S annual and S quenched and the definition of this C annual. So that's one thing. So we know that there is some C colorable somewhere here. So let me now show you, let me show what this, if you do the numerics, how it looks like. So, this is actually not the coloring problem. These are data for related problem, but it's not very important. Let's first look at the full lines. So that would be the probability that the given graph is colorable with a given number of colors. And these are just for graphs that are larger and larger as the color changes. And you see that it gets sharper and sharper. So in a sense, if you plot something like a probability that your sample acquired magnetization or something of that kind, it will look similarly. The x-axis, because I cut it everything. The y-axis is the probability, the x-axis is the average degree. Or this is a different problem, but think of the average degree. Okay? And so you anticipate that as n goes to infinity, that there is really a phase transition, that this will be crossing and becoming sharper and sharper, so that this, this definition here somehow makes sense. Of course, this is no proof. It could still be that there is not a sharp drop, that it's a crossover. And that's, people in math are puzzled about that till this day, basically. There is no generic proof that this C colorability actually exists. And then, computing its value, it's another issue. But even the existence of this number, that is a sharply defined number, is an open problem mathematically. Okay, so there is this thing. So there was a lot of things. But now, when people became really interested, really a lot in computer science, in graph coloring, that's related to this second set of curves. That's the time a given exhaustive search branch and bound algorithm, something that people would typically use in computer science to solve that problem, that's the time it takes to decide if that graph was colorable or not. And you see that it peaks around this threshold. And this is something that people got in computer science, that study computational complexity, got really excited about. Because from the algorithmic point of view, probably most of you heard about the concept of MP completeness that Cook established 45 years ago. And graph coloring is one of the first, 21 Cook's problems that were proven to be NP-complete. That means as hard, it's once I give you a solution, it's easy to decide if it's a solution, but to find a solution, you probably need, you need as many operations as you need for a big class of these problems, and people believe this is exponentially many. So that concept is well known, but for a long time actually in computer science, in the 70s and 80s, people believed that these instances that actually require exponentially many operations that are very rare and not easy to find. And that was based on some works that analyzed random instances which actually are on average easy. But and this was the work of Cheeseman, Kanevsky, and Taylor, that introduced this random ensemble of graph colorings and say, look, if we generate random graphs close to this average degree, they will be computationally hard. And that was the first time in history that people could generate at random easily instances that are computationally hard. And that got, many people developing algorithms and thinking about algorithmic complexity very excited. And that's basically also where our motivation comes from. Because, this is a nice mathematical game, but what's happening in this problem algorithmically? And this trouble with, when the question?
This entire story is for the Poissonian degree distribution, or it's general?
It could be different degree distribution of random graphs, but yeah, you need some randomness to define what's your x-axis to have some parameter that you change.
But it's
could
not
be.
contingent on Poisson.
No, it could be some, it could be regular graphs and then random regular graphs, then you just have discrete degrees, but you would have this kind of phenomenology. You could pick different degree distribution. You could basically, like all that I will be saying, you just take generic pk here. You probably need something like the second moment to be finite, not to have something completely crazy. If you had like really hubs, then it could behave differently. But say that you have P of k with a finite second moment, everything will be the same. The numbers will change, of course, but it's kind of universal. So, but things get even more striking, and that's somehow seen when you go to this limit when the number of colors is large. So it's actually quite easy to establish that when number of colors is large, then also the scaling of this C colorable must be twice number of colors, time logarithm of number of colors. And that's based on some, on the Chebyshev inequality. Here I computed the average of the Z. I could also compute the average of the second moment of Z, and then using Chebyshev inequality, I could put a lower bound on this C colorability number, and it would have the same leading order scaling, okay? So on random graphs are colorable up to average degree that is twice Q log Q, okay? Now take rather trivial algorithm that people actually can analyze, and that's the following thing. Just pick a random node, put it a random color that is not yet on its neighbors, and go on like that. And either you halt because you found a contradiction, or you found a valid coloring, right? So you can analyze this process, and without with some differential equation method established by Wormald some years ago, and you will find that this algorithm works when the average degree is smaller than half that, so Q log Q. Okay, why not, right? It's a very simple algorithm, as simple that you can even rigorously analyze how it works. It works half the way it possibly could. So far, no mystery. Now, the mystery comes that people worked really hard on improving that. And in the limit when Q is large, they could not find any other algorithm that would work. So there is this, so now I should, there is this big open problem. And I want to write this somewhere in big, but okay, I can probably erase this triangle. So, it's a big open problem when basically in computer science, like for all people that think about algorithms and computational complexity, is on random graphs, when Q is big, so, but, n to infinity first, is there algorithm that colors graphs of degree that is 1 plus epsilon q log q. So it takes few pages to prove that it's possible up to 2 q log 2, but 1 plus any small epsilon q log q, nobody has an algorithm that would be able to color graphs. So you see what I plotted there, that things get hard around the threshold. It's much worse than that. There is actually half of the, and when q is large, there is half of the colorable region where nobody has a clue what's the algorithm that would be able to do that. So it might be that there is no such algorithm, but that would imply that P is not empty, and that would imply a lot of things that nobody has any clue how to prove. So proving the converse, that would be very difficult. But okay, and nobody found an algorithm that would be able to do it. And that's a really big puzzle. So the main thing we want to understand here is there something happening at this q log q. What is there happening at this q log q physically? Okay, so I will not get to this in today's lecture, but in tomorrow's lecture. What is really happening at this q log q? Okay, so that's the end of the introduction for random coloring. So I think this next figure's okay. So I will not need this anymore, so if you can put it up, that's a good time. And did I want to say something more? No, okay, that's end of the introduction. So okay, just to summarize, graph coloring is a funny problem. Everybody can understand what's going on. We have graphs and colors, and we want to color them. Broadly, it's interesting mainly because of this conjecture, because it's a great playground for where the hard instances are, and everybody that is interested in the theory of algorithms, in the theory of computational complexity, which many of us are, should be aware and should be interested in this problem. Okay, so now where does so far there was no statistical physics. So let me just use like one blackboard to just formulate this problem as a problem of statistical physics. Not even one blackboard, probably just one line, right? Because all I need is the Hamiltonian. Once I have the Hamiltonian, everything is fine. So given the graph, so the graph that's given. So given the graph, the Hamiltonian will be sum over all the edges, and I will put a 0 here if the colors of the two nodes are different, and I will put a 1 here if the colors of the two nodes are the same. So I'm counting a penalty 1 for every monochromatic edge, and then the question of does there exist a valid coloring is equivalent to the question, is the energy of the ground state 0? Right? Is there an assignment of colors such that the energy is 0? And we were already anticipating here the entropy, so we could think of e to the Boltzmann measure being 1 over z e to the minus beta h of s. And this will be the temperature, but of course, if we want to talk about the ground state, we want to talk about beta goes to infinity, the 0 temperature limit that will be describing the proper colorings, and the number of proper colorings that will be the degeneracy of the ground state. So it might be that there is only one, that will not be very common. Either there is none ground state of 0 energy, or there is exponentially many for the reasons that we already mentioned. Okay, and okay, that's it. So now I wrote it, what it is mathematically. How would we call this in physics? Right? These colors would be Potts spins. When you have spins, the Potts model is when we have exactly these types of spins. So it's a Potts spin mal. And what's the interaction, right? We don't want them to be the same. So it's antiferromagnetic. Antiferromagnetic spin mal. Okay, doesn't look very horrible, right? It's just Potts antiferromagnet. What's the big deal? You should be able to say anything about that. Well, it's not as easy, because unlike in the Ising ferromagnet on a square lattice, which are probably the ferromagnet that you're the most used to think about, you have the lattice, and it's, if you take the odd elements of the lattice and the even elements, then you can transform the antiferromagnet to a ferromagnet, so there is no frustration in that case, right? But if you take antiferromagnet, even the Ising one on a random graph, you had these triangles here, there is frustrations. So even though it's not a disordered system, I mean, it's disordered in the sense that the graph is random, is disordered. The interactions are not disordered, but there is frustration. So actually, this will not be antiferromagnet physically, this will be a glass physically. And that's somehow what we will be talking about, in which sense it is a glass, and this will, anticipating something will be happening at this Q-log. Where did I put the Q-log? Here. So that's what we will be going after, what's happening in the phase diagram of this Potts antiferromagnetic spin model at the Q-log. That's it. But so far, okay, it's a statistical physics problem, but so far I said nothing. I just translated it, right? So now I want to do something. I have a bit more than half an hour to actually do something. So I will derive, what do we do? So, okay, one more thing. How do these graphs look like? Okay, that's important. So there is one important property of these random graphs that I didn't mention yet, but I should. And that's what we call that they are locally tree-like. So what does that mean? So tree is a graph that doesn't have loops. So this would not be a true, because there is this triangle, this cycle, that's a loop. But if I erase, say, this edge, then it would be a tree, because there is no cycle. So trees are graphs without cycles. Now what does it mean to be a locally look like a tree? That means if I go to some quite big distance from a node, walking by the neighbors, I don't see any cycles. Not too soon. So how do I see that random graphs have this property? So let's think about it for a while. How is this random graph constructed? I basically take a node and I connect it to an average C of other random nodes. Well, this will not create a loop with high probability. Let's go one more step, right? I connect, so I would have a node, and here I would connect to C other nodes, and then I would connect random nodes. So just a very hand-waving argument, when do I start crossing loop? When do I start closing loops? I will start closing loops when somehow the surface of the nodes, the number of nodes that I'm hitting on the surface is basically of the order of n. If it is much smaller, then with still decent probability, I'm not closing any loops, right? So if I take, at every generation, I have the number of nodes I'm hitting is the average degree, power L, where L will be the number of generations. And I said that relevant scaling here is when this starts to hit something of like n. So L needs to go something like logarithm of n divided by logarithm of c. Okay? So from this very hand-waving argument, we see that we starting closing loops when the distance is about log n. And n goes to infinity, log n goes to infinity. The distance at which we will be starting to close loops is quite big. So this is just hand-waving, but it can be made fully rigorous, and it's true as long as the second moment of this probability distribution is finite. This is a correct result, okay? The size of the shortest loop that goes through a randomly picked node is log n times some constant. So these graphs, they basically look like trees up to some really large constant. And that's somehow where the method that we will be using will kick in. So what I will do in the rest of today's lecture is that I will basically tell you how to compute this partition function, which is everything you need, because from this you compute the free energy by deriving it with different variables. You compute all the local magnetizations and all the things that you need to describe your system. How do you compute this partition function on trees? So that will be the rest of today's lecture. And tomorrow's lecture will be, is that correct or is that wrong? If your graph actually is not a tree, if it is only locally tree-like. So that's the plan. It's much harder, that's true. I will even make it harder. I will not even do it for this Hamiltonian, but I will say, okay, I have some probability distribution that will be product over some nodes of some function gi si times product over, not maybe even edges, but some like this e here will be hyper edges of some function fa that depends on s I such that I is in the neighborhood of A. So I will, the partition function that I will be computing will be even more general than that. And okay, indeed, if I send then beta to infinity, then I am back at this simpler question. But I want to build it generically because Florian will need it in his tomorrow's lecture, and I will need a non-trivial version of that to actually solve this problem. Okay, but this is not so. So that's why I will be, okay, so the goal here, okay, I forgot the partition function here. So there is some disorder here, like the graph, but I will not be writing it. So this is the Boltzmann distribution, kind of a generic. So I from 1 to n. Okay, let me write the 1 to n. What are these a's here? Before I had edges, but here, I'm representing the interaction graphs as kind of a hypergraph. So I just, instead of putting an edge, so these squares will be representing these edges. And in graph coloring, edges would be connecting only pairs of nodes. So for instance, I don't know, like this. Oh, sorry, only pairs of nodes. Like this or like this. Right? This would correspond to a graph on 5 nodes. This would be the same nodes, but now the edges, I just don't draw an edge. I draw an edge with the square in the middle. So in a sense, I think, oof, it's too far. Not a good choice of choosing. So with the graph here, I just put square in the middle of every edge. I could do that. I mean, why not, okay? But now the thing is that this square can be connected to more than 2 guys. It can be connected to 3 or to everybody, or, as I choose it. And anticipating the linear regression, that's a case where the square is connected to everybody, etc. So it will be useful to derive the things for this generic form. Okay. And now, of course, the fact that I put squares here and made it a factor graph, so this is called a factor graph. There's a whole part of inference, statistical inference, where problems are solved in the following way. You bring me a real-world problem, I build a factor graph representation of that problem, and then I just run some, black box machinery on that factor graph. So that's kind of a very, very useful tool to have in thinking about generic models in statistics, in statistical physics, in information theory, etc. Just, have a graphical model, a factor graph, and do things. And so what I will be deriving here is what I will call belief propagation. Belief propagation is an exact method on trees how to compute this partition function. Okay, so trees. So let me do this drawing that I need to somehow. Okay. So, right. So to compute the partition function, so let me define the partition function just to be sure what we are talking about. That's just the sum over everybody of this. This okay, or well, this one is the same thing. Okay, and now I will, so this is confusing. This is just the name of this guy, and I will erase most of this, needing it. So now, let me do this drawing. So what I'm doing here is just, I'm just drawing part of that hypergraph using the fact that locally it looks like a tree. So you know, it would continue here, and it would continue here, and it would continue above there. But if I just look how a neighborhood of some square A looks like, it would typically look like that. Of course, the number of neighbors A has, a number of neighbors J has, that's a parameter in this graph. So I chose like 4 here and 3 here, but it could be anything, okay? But somehow locally, things look like this. And now, the way I will do things, like, you know, why are trees easy? Trees are easy because if I condition on what's happening on this node, then these 3 branches are not communicating. They are not connected anywhere, right? Because this is a tree. And correspondingly, the corresponding probabilities are hence independent. And so to deal with them, I can write that the total probability is a product of these probabilities because they're independent. And this will lead to iterative process to compute the partition function exactly on a tree. So in order to write that, I will define some auxiliary partition functions. So I will start defining this, this kind of a notation that, well, at first it looks crazy. Like I have like 2 upward indexes with an arrow and a lower index. So okay, it will take you some time to get used to that, but let's hope that at the end of the 6 together lectures, you will be happy with these message passing notations. So this will be a kind of an auxiliary partition function. This is its definition. So this R, it's a kind of message that goes from J, okay, this is the J to A. So this is the R. So the R is running between this node, this circle J and this square A. And what it is basically the partition function of everything that is above J. So I'm summing over everything that is above J, so I write it also this way. I'm summing over all Sk such that K is above J. And the same thing here. So product over K, and here K is, it can be J and everything above J, of G, K, Sk, and also all B that are above J. So not only this B, but also this B, and also everybody that is above. So here I just include everything that is in the partition function that in this figure is above J. So product, and is the same factor. So FB and SL, and L is still in the neighborhood of B in this case. Okay, so that's one auxiliary variable. And then a second one that will be running between A and I, so here, and will also be related to the SI. Because you see, this guy depends on the Sj, because here I summed over all Sk that are above J, but not about Sj. But the Sj appears here, but it also appears here, right? If B here is really this neighbor on this neighbor, in its neighborhood there is J. So what I defined here depends explicitly on Sj, but not on the other spins. And similarly for this one, so here I will be summing over all Sj, where J is above A. So including all these and these, which I was not touching before. Okay, and the same thing here. So J, G, J, S, J, and here I do product over A and everybody above A, and B above A, of, again, FB, SL, which is in the neighborhood of B. So the notation probably looks very heavy, but the philosophy is that these are just auxiliary functions, partition functions, defined disregarding everything that is somehow below this arrow. And I define the one from J to A and the one from A to I. Now I will be writing how they are linked to each other and writing basically iterative equations between them. But is this notation somehow, well, it's probably not very clear, but are you at least okay with it? I mean, do you see what I'm doing here? At least broadly. Okay, cool. So if you're fine with that, then let's just start rewriting these things a little bit. Also, you don't probably see here. So let me write, what is this V equal to? So let me start splitting this V. So let me, pull part of the sum in front. So here I have this big sum over everybody that is above A, but let me split it. Let me split it into those that are immediately above A. So J that is really neighbor of A and is not equal to I. So this is this notation. And then let me split from this product the one where B is equal to A. So this FA that will then depend on the S, how should I call it, L whatever, and the L is in the neighborhood of A. Okay, so that's the thing that I pull in front. And then, okay, and once I did that, I realized that all the other terms that are there left, they basically come either from this branch or this branch or this branch. So I can write it as a product of these three things. So again, J that is immediately next to A and is not I. And so what is there left? So what is there left is now the sum over, SK. Now it will look horrible, but immediately after it will really simplify, where K is all above this J. And then, again, the same things as before. I need a product over all these Ks of the GK, SK, and the product over all, do I have B? Not yet. So all Bs that are above the J of this FB, and the spins here that are in the neighborhood of the B. Oof, okay. So I didn't do anything, I just rewrote this thing, pulling many things in front. And then I realized that what was left here is exactly the R. You see that? Is that true? Should be. Yeah, here K, here I should add J. Yeah, J is still here. I didn't pull it out. So this product is over J and all K that are above J. It's just as in the definition of the R, because that's the, okay. So okay, good, so things start to simplify. So this is R as J, J to A. So that's one thing, that's useful. And by doing a similar gymnastics, you can write that R as J, J to A, is equal to, again, pulling some things out and realizing that what is left is exactly the definition of V, you get this. Okay, so at one hand we have this, at that other hand, let me just rewrite it, we have this, SI, and here I just copy, should I just copy it? Okay, let me just copy it. SJ, FA, SL, LA. Product over J, R as J, J to A. So I have these two equations that are closed on the V and R's. See this, now, at the leaves, I can compute what V and R is from the definition because nothing is above, so I'm not summing over anything, so it's 1, right? Or maybe it's the G of K, if there is some, magnetic field on the leaves. So maybe it's the G of the leaf, or 1 if there is no magnetic field. And it depends. The R would be which one? One of them would be the field, the other one would be nothing. So on the leaves, I know what these things are from the definition. And then since it is a tree, I can just iteratively go down and compute all of them. And okay, it's nice. So how about then, okay. So there are two things. So first of all, these are partition functions. Partition functions are typically exponentially large. So if I actually want to do that in a computer, this will be some numbers that will be blowing, right? They will be exponentially large. So that's not very comfortable. I mean, this will end up to be an algorithm, actually useful algorithm. So I don't want to be running an algorithm that I have to treat with exponentially large numbers. So what would actually be really useful, and what would be the form of this belief propagation that we will end up using several times during these lectures is something that will be defined on these variables. So psi, it has the same indices as the v, but is the v normalized? Right, so these are partition functions. You see, these are sums of some positive or non-negative terms. All these things are typically some exponentials, so they are non-negatives. So all of these quantities that I'm defining and dealing with are non-negative, and hence, if I normalize this way, this can be interpreted as a probability, right, over these indices. So that will be one of them. Another one of them will be, of course, related to the R, but it will be related in the same way. It is exactly that R, except it is normalized in such a way that if I sum it over the components for every edge, then it sums to 1. So I define these messages. So this will be the belief propagation messages. And then, okay. Then to derive the equations, self-consistent equations between these phi and psi, what you need is you need just to plug these definitions into these equations. Right? So you can imagine doing that and then simplifying, and you get something that is related. So actually for the equations how to iterate these phi and psi, so let me start with the psi. So what you will end up with is you have some normalization here that I will define. J as J, product over B, J, so A. And this psi, Si. So I will write those, but then I assume that I lost everybody because these are so horrible expressions. So then I will spend some time bothering you about actually making sure that we understand these expressions because we will be using them quite a little bit. Okay, so the derivation, you can probably redo it, yourself calmly. There is nothing tricky about it. But what is important to understand is to understand the form. So these are the final equations. These are quite generic belief propagation equations where I didn't define these quantities z, but those are defined. Where can I write them? Well, let me continue. It's good that I have space. Those are just the normalization. So I could just say that, but since it is first time, probably many of you are seeing that, let me just define them explicitly. So the Zj is just sum over all S of whatever this thing is. J, and the Z, A to I, is just sum over all S. Sum over all is J around AI, FA, okay. And the same thing, I just copy there. Now these things are normalizations such that if I sum, okay, so to step back, okay, what did I write here? So now, we were deriving things for a tree, but now we could actually forget about the fact that it was a tree. We could interpret what these equations mean even for our original graph. And then tomorrow we will be discussing if that is reasonable and when it is reasonable. Okay? okay? Because a priori it's very unreasonable, right? So I agree with you. So let's postpone that, but let's just see what it means. So we define something that on every directed edge, on every edge from J to, this A that's the middle of the edge. So from J to, so A actually for the graph coloring would be IJ, for instance. And here it would be, IJ. So it's going from node J to the middle of the edge that is indexed A. And this one is going from the middle of the edge to the node I. And each of them is indexed by the color of the node. So it's a vector of Q components. We had Q colors, so these are vectors of Q components. They have non-negative elements, and the sum of their elements is 1. That's assured by the definition of this normalization, right? That's how I define this normalization here. And the way, that's the way the normalization is computing, and they are related to some potentials that live on the nodes, and that are somehow defined by the model. That's really part of the Hamiltonian, what these G's are. And then I am making a product over every neighbor of J, but not A. That's what this set minus A means here, right? So I'm making a product. Here we were going from J to A, so I'm making a product over everybody who is a neighbor of J, but not A, not the guy to which the message is being sent, of the other type of messages. And the other type of messages is, again, a vector of Q components with non-negative elements that sum to 1, that's assured by this normalization. And in order to compute it, it's slightly more complicated because there is this sum. And the sum is over the assignment of colors or spins or variables to all of the neighbors of A, again, excluding I. There is always this exclusion of the guy to which this message is going, of this interaction factor, FA, that is, again, defined by which model we are looking at, and that depends on the spin variables that are on the variables that are inside this interaction A. So for the graph coloring, this would be just the two neighbors, just the two ends of the edge. A would be the edge. Here I just wrote it explicitly, excluding the I, but putting it back here, because the I is, the whole message depends on SI, whereas here I sum over all of those. I could also, not put it here and not put it here, but this way it's maybe more explicit, like where this dependence comes from. This is J. And finally, a product over all these neighbors of the other type of messages. And that's it. When you want to run this as an algorithm, you just take these vectors, you put there some numbers that sum to 1 and are non-negative, and then you just iterate these things. You see now these are numbers between 0 and 1. So this is quite like, you can implement it easily in some distributed way. I give you the graph, I give you a prescription for the G and for the F, and that's it. That's a very, you can deal with any kind of I have what? 7 more minutes or so? Is that correct? Yes. So any kind of graphical model. Sorry? Yeah, but the normalization has this explicit prescription, right? So in the implementation, what I do, I just compute this for every Sj, then I sum them up, and that's the normalization. See, so updating one of these equations takes number of steps that is proportional to the number of neighbors I have. Not more than that. It's not a big deal. So computing this Z, maybe I should not call it, maybe I should not call it this Z. Okay, maybe I should call it, say, some other letter. Because this is not the global partition function. This is just some auxiliary variable that I need to iterate these equations. This has nothing to do with that. Well, it actually has something to do with that Z. That's what I will write right now, but it's not, it's not something exponentially large. It's another number between 0 and maybe degree or something like that, right? So, okay. If it is really first time that you see it, it must seem to you as a kind of an abstract thing, like, why do you do that, right? But you will see in the next 4 lectures that this is kind of the hammer. This is the hammer that people in computer science or statistics or information theory, some of them have it. They are bothered by many of the things about this tool being non-rigorous. And so maybe that's, that's slowing them down into using it in as many situations as they possibly could. So that's somehow our asset in statistical physics. This in statistical physics, okay, belief propagation is a name that comes from Bayesian statistics. In physics, actually, this would be called the cavity method. And it was developed by Mézard and Parisi in the 80s, basically. Or, okay, that's not even true. It was developed by Bethe in the 30s. So the Bethe approximation, when you solve the Ising model on the Bethe lattice, that's exactly this type of equations. So here they are really generalized to basically any kind of model. But the Bethe approximation is doing exactly that. So we should really go back to Bethe. But somehow the extensive use of these type of equations in applications outside of physics, that's due to Mézard Parisi, much later than that. Or also, okay, I could spend probably half an hour on the history of these things. So that's this. So now in the last, so there were some questions. I should take the questions. No more questions. So as in the last 5 minutes, I want to do, so I can put this as an exercise, just, so I want to do 2 things. I want to write finally the expression for the partition function, because that's what I promised, right? And I haven't write it yet. I just wrote some iterative equations for some auxiliary variables. So, okay, you can imagine that I will somehow be using that to compute the partition function, but I didn't yet. So let me do it. Now, I will not derive it. You can derive it as an exercise. It just goes to the same way. I mean, basically thinking about what would be the exact thing to do on a tree, you can persuade yourself that on a tree, this is an exact expression. Then on a graph, okay, that we will discuss next time, and next time if it is reasonable or not. So let me just write it though. So let me write the logarithm of the z divided by n. Do I want to divide by n? Probably, I don't care about divided by n. Then I write it Bethe, right? Because this is not necessarily the exact one, but that's somehow the Bethe approximation to the partition function. So how does that expression look like? So that looks like this. Okay, so it's a sum over all nodes of logarithm of some zi. Okay, now I wrote curl n, so I will continue with curl n. If then later on I start writing z again, it's probably okay. Log of curl n ij. Okay, so this is so far easy, but what's this curl n? This curl n is related to this guy. It's basically that guy. This was I or J? Now this was J here, but now I'm writing it with I, so the I should be here, S, with the only difference that now the product here is over everybody. Now I'm not excluding anymore the guy to which it goes, because I don't have any guy to which it goes, but otherwise it's the same expression, and this N, oh, gee, I'm writing this for the coloring specifically. Oh, okay. Let me just step back. So A and A, and then I should have plus minus. Okay, in general I have 3 terms. I was just writing it for the coloring. So, okay, so I have Ni, Na. Na is again the same thing as here, except I just don't put there the exclusion of the guy to which it goes, because it doesn't go anywhere. Fa, still the same. finally, this is the only one which is basically new, because that one I didn't define yet, and that's this guy. Psi s a to I, and psi s I to a. Okay, so to compute the partition function, what I need to do, I need to iterate these guys and find a fixed point. And then I take that fixed point, plug it into these expressions, which are related to these expressions, right? They're just like, here I don't exclude this guy, and here I don't exclude this guy, and this is a third one. And this I plug to this expression. So, okay, this seems, why should it be that? But when you think back about the tree, how these things come in is basically you build this tree somehow iteratively. And what this means is that here you are adding contributions of the free energy when you add the node I and its neighboring somehow half edges. This is the contribution when you add the hyper edge A and its neighboring somehow half edges. And you overcounted the half edges because each of them counted twice, so you subtract it. And that would be the contribution of this like half edge, this edge between A and I. So that's kind of the intuitive, why this expression has this form. And this can be made exact on a tree and okay, on a graph that we just assume that it's still reasonable. So anyway, if you implemented your algorithm where you found a fixed point of this is like additional, 4 lines of the code. No, not a big deal. So that's the Bethe free energy. And in the last minute, I just want to put this exercise, which I think is useful, just for you to make sure that you understood these notations, which are not very complicated, but one somehow needs to get used to them. And this will be, this is the generic form for a very generic Boltzmann distribution. But if we go back to the graph coloring, this is what we will do the next lecture. What do these equations become for graph coloring? So first of all, this GI SI for graph coloring is just 1. I don't have any local field on the nodes, right? And this Fij of SI Sj is just 1 minus delta Si Sj, just exponent of the delta when beta goes to infinity, right? If they are the same, the F is 0. I'm not happy. All the weight goes to 0 if I multiply by only a single one 0. And if they are different, then the F is 1, and I'm happy. I'm counting that guy in. Okay, so if you plug in Gi and Fi, and you also realize that if A contains only 2 neighbors, and I'm always excluding 1, then this sum is always only 1 guy. So I effectively really don't need 2 sets of equations. And I can really, easily close things on the Xi Sj, J to I, which will be, again, okay, I started to write Carl N, J to I, product over everybody around J, but not I, 1 minus Xi Sj, J to I. That's the belief propagation for the graph coloring, with this normalization being defined again the same way, is the sum of this guy over all these indices. Okay. So this looks much simpler than these 2 equations, right? And it's really, it should be, I really encourage you to take these equations and get to this form. Maybe some of you see it directly. I mean, it's not very complicated, but for all those of you for whom the notation is new, and somehow these products over all the neighbors, excluding 1, are, kind of get some time to get used to it. Just make sure you understand that for the graph coloring, from the generic form, you get this form. If you know how to do it, it's like 2 lines, but just for you to be sure you understand the notation. And if you don't understand, please ask me, because if the notation and what these Xi's actually mean and how you compute these normalizations and what these products are there for and these things, if you don't, you somehow don't see that from the generic form, then you will be lost for the next lecture and probably the one after as well. Yes? There is k, yes. So the k is j to I, and the product is over all k that are neighbors of j, but that are not I. Oh yeah, sorry. K to j. Thank you. Good. You see? You know, I'm sloppy, and you're starting to understand the notation. Good. That's good, but okay, but indeed, there is no escape, right? Here, there is a non-trivial dependence on the, here, on the Sj. The Sj is here. The fact that this right-hand side really depends only on the Sj, that's specific for the coloring. And then you will see when you plug this in, you will see how the other Sk's are, how the other S's go away, using the fact that when you sum these psi over the indices, you get 1. That's what we were saying. These are non-negative Q-component vectors. Their elements sum to 1. Okay, so this is the end. This is the exercise for the next lecture, not for Friday, because this will be needed already tomorrow. And just to give you a highlight for tomorrow, you basically spend the whole tomorrow arguing what we can get from these equations for the random graph coloring. And when we start understanding what's somehow okay and what's not okay, we will define the version of the coloring that we'll call the planted coloring, that on one hand will help us to understand what's going on and what's the relation to glasses and where this Q log Q in the algorithmic hardness is coming from. But also, in the end of the lecture, we will interpret that planted coloring as a statistical inference problem and connect to all that Florian was talking in the morning. And you know, some of these concepts that he was developing, we will basically say, what does it mean for the planted coloring? And from what we understood already about coloring, what can we say about the planted coloring as an inference problem? And then we will generalize it to a nice class of inference problems that are basically related to clustering of networks. And we will see that the concepts, you know, that somehow are interesting there that we can understand from statistical physics that are really related to graph coloring. So we will somehow, you know, at this, partially give an insight about this algorithmic puzzle, and then we will move to the inference version of these problems and talk more about inference and information theory and what's information theoretically optimal inference, etc., in these type of problems. So that's just okay. That's it. Thanks.